G'day, in this video we're going to be looking at evidence that exists for the identity and properties of the electron. We're going to be looking at Millikan's oil drop experiment. So we're going to be finishing off dot point 8.2.1, which looks at the experimental evidence which allowed us to identify the properties of the electron. And we're going to be looking at Robert Millikan's oil drop experiment and the methods that he used to figure out the charge and the mass of the electron. And once we've done that, we're also going to be outlining the contributions made by his work. Millikan conducted an experiment with the aim of determining the charges of particles of oil. Once he knew the charges of particles of oil, he was hoping that he could figure out the charge of an electron and use Thomson's mass to charge ratio to figure out its mass as well. So what did he do? An oil spray was delivered into a chamber by something called an atomizer, essentially something that can separate the oil into fine droplets. And the droplets inside the chamber dropped into the lower part of the container. However, there was only a small space through which these particles of oil could drop. Therefore, the likelihood of one of these particles dropping through was quite low, meaning that effectively you could separate out the atomized oil and analyze one particle at a time. In the lower chamber, X-rays were emitted, which removed electrons from surrounding air particles. These free electrons were able to attach to the droplet and give them charge. Now, while Millikan didn't understand the idea that the X-rays were dislodging the electrons, he did understand that the X-rays were able to charge the oil, and in particular, provide them with negative charge. So once this charged particle was in the lower chamber, it was experiencing two forces: a gravitational force due to the gravitational field of the Earth, as well as an electric field which was applied to the droplet as well. This electric field was designed to oppose the gravitational field. If Millikan could alter the electric field so that the charged oil particle was suspended, he could assume that the force due to the electric field was equal and opposite to the force caused by the gravitational field. Using this concept, we can derive a formula to calculate for Q. From our data sheet, we know that the electric field strength of parallel charge plates is equal to the voltage of the plates divided by the distance between them, and that the force from electric field is equal to the charge of the particle experiencing the force multiplied by the electric field strength. By substituting in the right-hand side of the first equation into the right-hand side of the second, we get the equation Fe is equal to QV on D. And we also know that the force due to gravity is simply equal to mg. From here, we can equate the two formula and solve for Q. G is a standard value, and the distance between the plates as well as its voltage are quite easy to measure and account for. The tricky bit is knowing the mass of the droplet. So how did Millikan know what the mass of the droplet was? Well, he didn't use a scale, but he was able to determine the terminal velocity of the droplet and analyze it to figure out what its volume and density was, and that then revealed its mass. The process is quite involved and complex, so it's something that we might unpack a little bit in class, but is not going to be within scope of the syllabus dot point nor this video. Millikan repeated this experiment with countless charged oil droplets, yielding him a very extensive data set. And what he noticed was that his calculated charges existed in clusters. What this meant was that the droplets of oil did not take on a continuous series of charges. Instead, it was picking up quantized packets of charge, suggesting that the charges were attaching to the droplet of oils as particles with an exact amount of electric charge. In other words, electrons. What he concluded was that the charge of any of the oil droplets was equal to the number of electric charges picked up multiplied by the charge of these individual charged particles, the electrons. What he noticed is that the smallest difference of charge between any cluster was negative 1.59 times 10 to the negative 19 coulombs, which is only just slightly lower for the current value for the charge of an electron. His assumption was that the smallest difference that he could find between any cluster would therefore be the charge of one of these electrons, and that the difference in charge between their two clusters was simply that the cluster of oil droplets with the larger charge had picked up one extra electron compared to the cluster next to it. So now that Millikan had determined the charge of an electron, he was then able to use Thomson's charge to mass ratio to calculate for the mass of the electron. And this mass was quite close to the standard mass of an electron we know and understand today, which you can find in your data sheet. Thank you very much, everyone. In the next video, we're going to be looking at more evidence for subatomic particles, but we're going to be looking at nucleons, the protons and the neutrons inside the nucleus of an atom. We're going to be unpacking the Geiger-Marsan experiment. But until then, have a good one.